Today we are going to discuss about applications of 555 timer IC when it is operated in its astable mode. There are three main important applications, and that applications are: first one, it can be used as a FSK generator, then it can be used as a Schmitt trigger circuit, then it can be used as a pulse position modulator. Let's now consider these applications in detail. Let's first consider the application as an FSK generator. We know FSK is frequency shift keying, which is a digital modulation technique. And this is the connection diagram of 555 timer IC as an FSK generator. Here this 555 timer IC is wired as an Astable Multivibrator circuit. Then when we consider an FSK modulation technique, which is a digital modulation technique, that modulating input signal consists of only two values, logic 0 or logic 1. And this FSK is a technique in which when that modulating input signal is logic 0, then that is represented by using one frequency, and when that modulating input signal is logic 1, that is represented by using another frequency. Okay, so when we design an FSK generator circuit, when logic 0 comes at the input, we need to get a particular frequency at the output. Let that frequency is F0. And when the modulating input signal is logic 1, we need to get another frequency at the output, and let that frequency is F1. Okay, by using this arrangement, we can obtain such a two different frequencies at the output depending upon the modulating input signal. Let's now look how this circuit works. When we compare this circuit arrangement with our normal Astable Multivibrator circuit, here we can see this Q1 RC portion is connected in addition, and here we can see this Q1 RC portion comes in parallel to this RA section. And this Q1 is a PNP transistor, and to the base of that Q1 transistor, that modulating input digital signal is applied. Okay, and here this RS is our source resistance, and which is very small. Now when the modulating input signal is 1, this transistor Q1 is in its off state, because this transistor Q1 is a PNP transistor. So when a high value is applied to its base, the transistor Q1 is off, hence no current will flow through this Q1 RC portion. So we can neglect this Q1 RC portion when the input signal, when that modulating input signal is high. Okay, then this circuit will work as normal Astable Multivibrator circuit, and hence we will get the output frequency as 1.45 divided by RA plus 2RB into C. We have already derived this equation in our previous classes. You can go through that video class for the derivation of this equation. Okay, then what will happen when the modulating input signal is 0? When the modulating input signal is 0, this transistor Q1 goes to on state. Okay, hence a current will flow through this Q1 and RC, and we can see this Q1 RC section comes in parallel with this RA resistance. Okay, then the resistance of this Q1 is very small, hence we can neglect that resistance value. Hence this RC resistance comes in parallel to this RA resistance when the modulating input signal is 0. Okay, so now the effective resistance between these 2 points is RA parallel to RC. Okay, hence the output frequency will be 1.45 divided by RA parallel RC plus 2RB into C. So in the place of this RA, here RA parallel RC comes when the modulating input signal is 0. Okay, so these two frequencies are different. So when the modulating input signal is 1, we will get this F1 frequency at the output, and when the modulating input signal is 0, we will get this F0 at the output, and that is the idea of FSK modulation. Let's now consider the application as Schmitt trigger circuit. This is the connection diagram of 555 timer IC as Schmitt trigger circuit. And here this 555 timer IC works in its astable mode. Okay, and here we can see that 6th and 2nd pin are shorted, and a VCC by 2 voltage is applied to that point by using this R1 R2 resistive network. Here we can see this R1 and R2 resistors are equal valued resistors, and hence the voltage across the R2 resistor will be VCC by 2. Okay, and hence at this point we will get a VCC by 2 voltage, and a sine wave is also applied to that point. Okay, when we compare this circuit with our normal astable multivibrator circuit, that capacitor section is here replaced by using this sine wave VCC by 2 arrangement. Okay, and hence the instantaneous voltage of the sine wave plus VCC by 2 voltage appears at the 6th and 2nd pin here. Okay, now we know in Schmitt trigger circuit, its output triggers when the input sine wave crosses the upper threshold level and lower threshold level voltages. That means when the input sinusoidal signal crosses its upper threshold level, then the output changes from its one state to another state, and when the input signal crosses its lower threshold level, then the output changes from that state to previous state again. Okay, and that will continue. Here also we can see when the sinusoidal voltage plus VCC by 2 voltage exceeds the 2 by 3 VCC voltage level, then the output changes from its high state to low state. And when the sinusoidal voltage plus VCC by 2 voltage goes below 1 by 3 VCC voltage, then the output changes from its low state to high state. Okay, so here that 2 by 3 VCC voltage appears as the upper threshold level, and 1 by 3 VCC voltage appears as the lower threshold level. Okay, and this is our input signal. When this input signal plus VCC by 2 voltage exceeds that upper threshold level value, that means that 2 by 3 VCC voltage level value, the output changes from its high state to low state. And when the sinusoidal signal voltage plus VCC by 2 voltage crosses our lower threshold voltage value, that is our 1 by 3 VCC voltage level, then the output changes from its low state to high state. Let's now consider the working with the help of waveforms. This is our input and output waveforms. We know when the VCC voltage is supplied to the astable multivibrator circuit, that 2 by 3 VCC voltage is present at the inverting terminal of the upper comparator, and 1 by 3 VCC voltage is present at the non-inverting terminal of the lower comparator. And we know when the voltage at the 6th pin goes above that 2 by 3 VCC voltage level, the output changes from its high state to low state. And when the voltage at the 2nd pin goes below that 1 by 3 VCC voltage level, the output changes from its low state to high state. That is the normal working of astable multivibrator circuit. Okay, and here we can see to that 6th and 2nd pin that sinusoidal input signal is applied, and also a VCC by 2 voltage is present by using this R1 R2 resistive network. Okay, hence the effective voltage at the 6th and 2nd pin is VCC by 2 plus the instantaneous voltage of this sinusoidal signal. Okay, so that sinusoidal signal is shown here. Since here a VCC by 2 voltage is present, this sinusoidal signal is riding on that VCC by 2 voltage, or we can say that sinusoidal signal is actually clamped by using that VCC by 2 voltage. Okay, and when that combined voltage of VCC by 2 plus that instantaneous voltage of sinusoidal signal goes above that 2 by 3 VCC voltage level, then the output changes from its high state to low state. And when that combined voltage of VCC by 2 plus instantaneous value of the sinusoidal signal goes below that 1 by 3 VCC voltage level, then the output changes from its low state to high state, and that will continue. So this 2 by 3 VCC acts as our upper threshold level, and this 1 by 3 VCC acts as our lower threshold level. And here this VCC by 2 voltage actually comes in between this 1 by 3 VCC and 2 by 3 VCC. For an example, consider VCC is 15 volt. When VCC is 15 volt, the 2 by 3 VCC voltage will be 2 by 3 into 15, and hence that is 10 volt, and 1 by 3 VCC voltage will be 1 by 3 into 15, and that is 5 volt. And what is VCC by 2 value? That VCC by 2 will be 15 by 2, that is 7.5, and this 7.5 is in between this 5 volt and 10 volt. Okay, so here this 7.5 is in between this 5 volt and 10 volt, and this sinusoidal signal is riding on that 7.5 voltage. Okay, then by changing this voltage at this point by using different resistor values, we can change the time at which the output triggers. The advantage of this Schmitt trigger circuit is that it simply converts the sine wave signal into square wave signal of the same frequency. Hence, this circuit can be used as a wave shaper. Let's now consider the application as pulse position modulator. This is the connection diagram of 555 timer IC as pulse position modulator. When we compare this circuit arrangement with our normal Astable Multivibrator circuit using 555 timer IC, the only difference is that to that fifth pin, the modulating input signal is applied here. In the case of normal Astable Multivibrator circuit, this fifth pin was connected to ground through 0.01 microfarad capacitor. But here, to obtain the pulse position modulator, to that fifth pin, the modulating input signal is applied and all other connections are same. Now let's consider the input-output waveforms of this circuit. This is our modulating input signal applied at the fifth pin, and here we are considering a triangular waveform as the input, and this is our output signal that is obtained at the third pin. And here we can see when the modulating signal is increasing, the time duration in which the output remains in its high state goes on increasing, and the time duration in which it remains in its low state goes on decreasing. Okay, so here we can see when the input signal is increasing, this width goes on increasing and this width goes on decreasing, and we will get the maximum on time duration when the modulating signal is at its positive peak value. Okay, and during that time the low time duration is at its minimum value. Okay, and when the input signal, when that modulating input signal goes on decreasing, here we can see the time duration in which it remains in its high goes on decreasing, and the time duration in which it remains in its low goes on increasing. And at this negative peak of the modulating input signal, here we can see the duration in which it remains in its low state is at its maximum, and the duration in which it remains in its high state is at its minimum value. So here we can see when the modulating input signal goes on increasing, the width of the pulses also goes on increasing, and when the modulating input signal goes on decreasing, the width of the pulse also decreases. Okay, and when we consider these pulses, its trailing edge is actually proportional to the instantaneous amplitude of our modulating signal, because the width of the pulse is changing according to the instantaneous amplitude of the modulating signal, and hence we can see this trailing edge of the pulse is changing according to the instantaneous amplitude of the modulating signal. Okay, and hence the position of the trailing edge is proportional to the instantaneous amplitude of the modulating signal. Let's now try to understand how this width changes according to the instantaneous amplitude of the modulating signal with the help of the functional diagram. This is the functional diagram of an Astable Multivibrator using 555 timer IC, and when we need to use this as a pulse position modulator, we need to connect that modulating input signal to this fifth point, and this capacitor section is not present. Okay, and here a triangular wave is applied to this fifth pin, and what will happen when that triangular voltage is increasing? To understand that, consider an example. Consider the VCC voltage applied here is 15 volt. Then here we have 2 by 3 VCC voltage. Then 2 by 3 into 15, that will be 10 volt. And here we have 1 by 3 VCC voltage, that will be 1 by 3 into 15, that is 5 volt. Okay. Then when we consider a normal Astable Multivibrator circuit, in that the fifth pin was connected to ground through 0.01 microfarad capacitor, and in that case the upper comparator triggers when the voltage across the capacitor goes slightly greater than this 2/3 VCC voltage or this 10 volt. Okay, and the output changes from its high state to low state. And then the lower comparator triggers when the voltage across the capacitor goes slightly less than this 1/3 VCC voltage or 5 voltage, and then the output changes from its low state to high state again. Okay, now in this pulse position modulator circuit, the modulating input signal is applied to the fifth pin. Okay, now consider that the voltage at the fifth pin or the modulating input signal is increasing in the positive direction, and consider the instant at which the voltage at the fifth pin is 2 volt, and we can see that 2 volt directly appears at the inverting terminal of the upper comparator. So when a 2 voltage comes at the fifth pin, the effective voltage at the inverting terminal of the upper comparator will be this 2 plus 10, 12 volt. Okay, so now the voltage at the inverting terminal is increased to 12 volt. Then this upper comparator will trigger only when the voltage across the capacitor goes slightly above this 12 volt. Okay, so that time duration is increased. Okay, when we consider the normal astable multivibrator circuit, this upper comparator trigger when the voltage across the capacitor was slightly greater than 10 volt. But now when a 2 voltage comes at this fifth pin, the voltage at the inverting terminal is increased to 12 volt, and now this upper comparator will trigger only when the voltage across this capacitor goes above that 12 volt. Okay, so that time duration is increased, and hence the time in which the output remains in its high state is also increased, and hence the width of the pulse is increased. So when the voltage at the fifth pin goes on increasing, the voltage at the inverting terminal of the upper comparator also goes on increasing, and hence the time taken by the capacitor to cross the voltage at the inverting terminal also goes on increasing, and hence the time duration in which the output remains in its high state goes on increasing, and hence the width of the output pulse goes on increasing when the voltage at the fifth pin goes on increasing. Now due to this 2 volt, the voltage at the non-inverting terminal of the lower comparator will also increase. We can calculate the effect of this 2 volt at this point by using the voltage division rule. Consider this resistive network. When a 2 voltage appears here, then the voltage at this point will be the 2 into 5 divided by 10. Okay, so that is 1 volt. Okay, so when a 2 voltage comes here, an additional 1 voltage will appear, and hence now the total voltage at this point is 5 plus 1, 6 volt. Okay, and what will happen when the voltage at the non-inverting terminal of the lower comparator is increased? When the voltage at the non-inverting terminal of the lower comparator is increased, this lower comparator will trigger early, because we know this lower comparator triggers when the voltage at the second pin goes below than the voltage at the non-inverting terminal of the lower comparator. And in the case of normal astable multivibrator, the voltage at the non-inverting terminal was this 1/3 VCC or 5 volt. Okay, but now when a 2 voltage comes here, the effective voltage at the non-inverting terminal of the lower comparator is now 6 volt. Okay, so when the voltage across the capacitor goes below that 6 volt, this lower comparator triggers. Hence the lower comparator triggers early in this case, because there is no need for the voltage across this capacitor to go below the 5 voltage. When the voltage across the capacitor goes below the 6 volt, the lower comparator gets triggered. Okay, so that lower comparator will trigger early, and hence that duration in which the output remains in its low state gets reduced. Okay, hence the time duration in which the output remains in its low state is reduced when the voltage at the fifth pin goes on increasing. And when the voltage at the fifth pin goes on decreasing, the opposite action will occur. Okay, so when the voltage at the fifth pin goes on decreasing, the time duration in which the output remains in its high state goes on decreasing, and the time duration in which the output remains in its low state goes on increasing. Okay, so depending upon the voltage at the fifth pin, the width of the pulse changes, and hence the position of the trailing edge changes according to the instantaneous amplitude at the fifth pin, and hence we will get a pulse position modulated output signal here. Let's now try to understand that working with the help of this timing sequence. This is the timing sequence of normal astable multivibrator. Then in our example we considered that VCC is 15 volt, and hence 2/3 VCC is 10 volt and 1/3 VCC is 5 volt. Okay, so in the case of normal astable multivibrator circuit, when the capacitor voltage crosses that 10 volt, the output changes from its high state to low state. Then in the case of pulse position modulator circuit, to that fifth pin the modulating input signal is applied, and then consider that modulating input signal is increasing in positive direction, and consider the instant at which the voltage at the fifth pin is 2. Okay, when 2 voltage appears at the fifth pin, then at the inverting terminal of the upper comparator, now the voltage is 10 plus 2, 12 volt. Okay, and that is greater than this 10, so consider this is that point. Then this capacitor need to charge towards that 12 point, and the upper comparator triggers only when the voltage across the capacitor crosses that 12 volt. Okay, so when the capacitor voltage is slightly greater than that 12 volt, then the upper comparator triggers and the output changes from its high state to low state. So the output will remain in high state till this time duration. Okay, so from here to here the output will remain in its high state, so that duration is increased, or we can say the width of the pulse is increased. Okay, so when that modulating input signal goes on increasing, the width of the pulse also goes on increasing. Then due to that 2 volt at the fifth pin, the voltage at the non-inverting terminal of the lower comparator rises to 6 volt. Okay, so let that level is this one. So now the capacitor is discharging from this point, and during discharging, when the voltage across the capacitor goes below that 6 volt, the lower comparator triggers and the output changes from its low state to high state. Okay, so here there is no need for the capacitor voltage to go below this 1/3 VCC level or this 5 volt. Okay, and the lower comparator triggers when the voltage across that capacitor goes below this 6 volt. So the lower comparator triggers early. Okay, in the case of normal astable multivibrator, the lower comparator triggers only when the voltage across the capacitor goes below that 1/3 VCC level. But here when this 2 voltage appears at the fifth pin, then the voltage at the non-inverting terminal of the lower comparator increases to 6 volt, and hence the lower comparator triggers when the voltage across the capacitor goes below that 6 volt. Okay, there is no need for the capacitor voltage to reach up to that 5 volt, so it triggers early. Okay, and hence the output changes from its low state to high state at this point, and hence this width is decreased. So when the voltage at the fifth pin goes on increasing, the time duration in which the output remains in its high state goes on increasing, and the time duration in which it remains in its low state goes on decreasing. And when the voltage at the fifth pin goes on decreasing, the time duration in which it remains in its high state goes on decreasing, and the time duration in which it remains in its low state goes on increasing, and hence we will get the output like this. Okay, so here we can see when the modulating input signal goes on increasing, that pulse width goes on increasing, and we will get the maximum pulse width for the maximum amplitude of modulating input signal. And when the modulating input signal goes on decreasing, the width of the pulse goes on decreasing. And here we can see the trailing edge is directly proportional to the instantaneous amplitude of the modulating signal. The position of the trailing edge of these pulses are changing depending upon the instantaneous amplitude of the modulating signal, and hence here we will get the pulse position modulated signal.